Thanks, everyone. I'm Dave Epstein, and with Dídac Surís, I'll be presenting some work on learning to learn words from visual scenes. I want to start off by talking about some stuff that's very different from what Professor Tenenbaum just discussed. It's actually, what can we do with stochastic gradient descent? How far can we take stochastic gradient descent? Of course, it's a very different way to think about these problems, but I think it's informative and it's representative of kind of a whole line of work that's also interested in the same questions. So one state-of-the-art approach that is interested specifically in the problem of modeling vision and language jointly, one approach that's gotten very popular recently is building on success that people have seen in the natural language community. And you take an input sentence, you mask out a word from the input sentence. In this case, that word is stir. And the model is tasked with reconstructing or predicting this word. So this approach basically has in some variant or another existed for around a decade. BERT made this specific variant quite popular. And in the last year or so, people have added image tokens as input to this model as well. And some variant of this architecture sits on the top of the leaderboard for basically every vision and language task that the computer vision community seems to be interested in. So a natural question to ask then is, how far is a model like this from the linguistic skills of, say, a 3-year-old, of a toddler? Of course, the answer, I think, is something that we could all instantly guess. It's quite far. It's very far. But we're interested in 3 specific axes along which we think there's significant progress to be made, and that we think the tools that we have in machine learning can tackle. So the first axis that I think is interesting is the sample efficiency. 3-year-olds are estimated to hear around between 10 and 40 million words by the time they reach that age, whereas all of these state-of-the-art models that are breaking records on a bunch of different tasks are looking at orders of magnitude more data than that. And this, of course, indicates something I think we already are getting at, and Professor Tenenbaum is getting at, that the learning mechanisms are very, very different. So the learning mechanism of a child is much, much more nuanced and much more powerful right now than the learning mechanism of a stack of transformer models. Another thing that is interesting is, let's see, skip a slide. Another thing that's interesting is the model's generalization ability. So compared to a child, the models like this really struggle to generalize. So for example, here on the right-hand side, we have a video which is kind of a realistic scene, a cluttered scene, not a toy scene, where someone is cutting a carrot with a knife, and the model has been trained on knives, so it's able to recognize that there's a knife going on here, and the model's predicting the word correctly. It's shown in green. On the other hand, on the bottom, the model is unable to understand that there's a knife being washed. Instead, it thinks that it's a pan being washed, and so it can't generalize, even though it's the same type of object. And it can't do this because it's never seen this composition. It's never seen the combination of the action of washing and the tool of the knife. So it's just not able to generalize. On the other hand, 3-year-olds, and studies have shown this since the 70s, if not earlier, are really, really able to do this generalization. So in this kind of toy example, there's a preschool classroom, which is very cluttered, has a lot of interesting stimuli. And yet the children at 3 years or even at half of that age are able to understand that there are 2 tables in this scene. There are more, but they're able to identify that these 2 things in the middle are tables, despite the significant variation between them. So despite the fact that one of them is blue and round, the other is kind of gray and rectangular, their pose is slightly different, and so on. The viewpoints are slightly different, but children are still able to generalize and understand that these are both tables. And this takes me to the final axis that I want to suggest, which is this ability to learn new words. And this is something that the previous speakers discussed. I think we learn on average 1 new word a day, if not more, for the first few years of our lives. And it's really a frenzied pace of word acquisition. And it's something that somehow we're effortlessly able to do. So in this toy example from a paper from 12 years ago, and of course this has been studied by Tomasello and many others before, a set of new objects is shown to a child, and one of them is given a new name, a zup. And then a new set of objects, which varies slightly from that old set of objects, is presented, and the child is able to point at the object that ostensibly belongs to the same category when asked, where is this up? On the other hand, a vision and language model, according to the formulation that we're considering, doesn't really have this ability or this mechanism to learn new words. It's trained on kind of a fixed vocabulary, a fixed embedding matrix of words, And if a new word comes in, it's not in that matrix or it's never been seen before, the model has no notion of acquiring a new word after it's been trained. And this is very unnatural, I think, compared to the way that we are always learning new words. If a new word comes up today in a presentation, we'll learn it pretty well, even though none of us are 3 years old. So what is the insight that I think we can draw? Of course, there's a lot of insight to draw, and this is kind of very loosely speaking, but one is that we're very powerful, even at a young age, at learning from vision and from language context. So we're able to use the context around us, the various sensory inputs, to learn very, very fast. And throughout this process, we kind of learn from experience to build this strategy to acquiring language from ambiguous input. So when we see kind of overwhelming or complex or somehow unclear input, and Quine has the famous example of the gavagai, which is kind of a crowded scene where you could be referring to either a rabbit or grass or a part of the rabbit. How do you disambiguate? Well, somehow we learn a strategy for doing this. And finally, kind of a more technical point is we can test for language abilities by asking children to point to the object that's being tested. So they don't have to be able to say it themselves, but if they understand it, we can just ask them to point. And that's something that will come in handy later. So to kind of go back to the concrete machine learning formulations, what we're interested in doing is learning to learn words. Why are we interested in doing this? Well, what we think makes sense is to go from a paradigm where the goal is to just learn the definition of a word, learn what the word stir means, for example, in this example. It's more interesting to learn how to learn what stir means. So given this information, given these stimuli, so to speak, how do we learn what the word stir means? How do we learn a policy to acquire the word stir? And this, of course, is something that can generalize much more readily to different words and to even learning new words, as opposed to just learning some fixed word definition, which will not help you with other knowledge. So to really talk about the meat and potatoes of the approach, Dídac will pick up from here and explain how we try to address these concerns.
So because we want to learn how to learn, we use meta-learning. So we formulate every task in this meta-learning setting as a language acquisition task. And as usual, every task consists of a meta-learning meta-training set and a meta-testing set. In this slide, we show an example of the task that we call an episode, which contains some training examples and a test example where the test evaluates the language acquired from the training examples. In this specific episode, the language acquisition task consists in acquiring the word chair, which is a new word that the system has never seen. So then the ground truth for the test example is the word chair. But how do we actually conduct the meta-learning? Well, the way we do it is by learning in the forward pass. So the meta-learning is just a forward pass of the entire episode through the transformer. And the transformer is a good architecture to perform this learning because it can capture the pairwise relationships between the elements in the dataset. Then in order to test that the model has learned the word chair in the forward pass, we use pointing. So we require the system to point to the correct word, in this case, chair. Pointing is basically performing the meta testing in our system. And it tests how well the system has acquired that language. And then this pointing is the loss we use to train the model. We train the model on many such episodes. So you can imagine a distribution of episodes where each one corresponds to a meta-learning task. And when you have many episodes, you can generate them in different ways to target different types of language acquisition. The first example is the one we showed before, where the model has to acquire a new word. And the second example implies not learning a new word, but learning a composition of words. So in this case, the model has to learn to compose the words stir and paneer in order to predict stir paneer. This way, the model has to learn how to do a compositional reasoning. So after the system has been trained with all these episodes, we can see how it performs on new episodes, on new language acquisition tasks. In this case, the episode contains a new word, that is avocado, and the test consists in predicting this word avocado, which is a word that the system has never seen during training. And we show that the predictions of the model here, where the darker the arrow, the more confidence the model gives to the prediction. So we can see that in this case, the model predicts correctly avocado. The previous example showed the new noun acquisition, but we also show similar examples in this case for new verb acquisition. Here in this case, the model correctly acquires the word gather, which has never been seen during training. We can also show that our approach obtains very good qualitative results. Here we show accuracy values when predicting new words. The baselines are BERT and BERT plus vision, which are trained to produce good contextual representations. So they have good results, and adding vision really helps improving the accuracy. But when training with our method, the accuracy at predicting new words improves considerably. And these results are for the Epic Kitchens dataset, which we found that it was the most challenging one that we tried, but we also obtained similar results for the Flickr dataset. We also look at generalization to new compositions of words. We define new compositions, which are green in this graph, as those sentences that contain pairs of words that have appeared during training, so they are not new words, but they have never appeared together during training. And we define seen compositions, which are blue in the graph, as those sentences that contain pairs of words that have appeared together during the training. In this case, because the words are not new, at this time we just input a single sample, not an entire episode. And a BERT baseline does not perform very well in this task, and especially the gap between seen and new composition is very significant. And then when adding vision, the system performs better, but still the gap is very important. And this makes sense that these baselines are not very good in new compositions. It makes sense because they are trained just to maximize the likelihood on the training data. And new compositions are slightly outside of the training data. So then our method manages to get the best results in both seen and new compositions. But most importantly, this gap between the seen and new compositions is close considerably compared to the baselines. And this kind of suggests that our method, our training method, is actually better generalizing than seen scenarios, as it reduces this generalization gap. And again, this makes sense that generalization is better because we explicitly teach the model how to generalize better, which is the main point of the paper. Finally, we also look at what the model is doing. So we conduct a few qualitative experiments that suggest a very high interaction between language and vision in our system. And here we show one of them. In this experiment, what we do is we block out different regions in the input images according to some region proposals. And then we evaluate how much worse the prediction is when predicting the word in yellow, which is a ground truth. So first we mask out one region in the image and evaluate how much worse the prediction is compared to not blocking any region. Then we independently mask out another different region in the image and evaluate again, and so on for different regions in the image. The region we show in yellow is the one that blocking it hurts the prediction the most, and therefore it's the region that is most related to the word that we want to predict. So as we can see, the yellow regions and yellow words have a high semantic correspondence, which suggests that even though we don't use any training labels, visual grounding emerges during this training. And that's it. Thank you for your attention, and we'll be happy to answer any questions.